The most important ingredient in conditional probabilities is common sense. But as is usually the case, common sense requires a little prodding. So let's just go along and see what happens. Sort of roll with it. Let's say we have a box, and in the box are 5 cubes, 3 white cubes and 2 black cubes. And I mix them around, I close my eyes, and I stick my hand in and I pull one out. What is the probability that that cube will be white? Well, the answer is 3/5, because 3 out of 5, they're equally likely, they're the same size, I can't see them, they're equally likely to be any one of them, and 3 out of 5 are white. The probability is 3/5, 3/5. The probability of a black one is 2/5. Okay? No problem, everyone understands that. So what? What happens if one of the white balls falls out? Well, if one of the white balls falls out, then there's only 4 balls left. And the 4 balls are such as cubes. They're not balls, they're cubes. 4 cubes left, and 2 of them are white, 2 of them are black. The probability of white is 1/2, and the probability of black is 1/2. And the way we say it is the following. We say the probability of a white one, given that one white one wasn't there. One white one's not there in the box. That means only 4 are left, 2 whites, 2 blacks, is 2 out of 4, or 1/2. And the probability that the black one is not there, given, by the way, this line up and down stands for given. This is a straight up and down line, and it stands for the word given the condition that. Given the condition that 1 is not there. Given the condition that 1 white one is not there, 2 out of 4 are black, and therefore the probability is 1/2. Knowledge is power. Knowledge can change probabilities. What do we know? We know that 1 is not there. We know a condition. A condition can be used to change probabilities, as it did here. Probably went from 3/5 and 2/5 to 1/2, 1/2. The conditional probability is written this way. There's a line here before the condition. Probability of an event given a condition. Given a condition. Okay? This is called a conditional probability. We have what's called a prior probability, which is the probability of the event without the condition. Now, there are several names given to these things. This is also called the marginal probability. And this conditional probability is also called the posterior probability. And the reason, if you say this is prior, meaning this is the probability of the event before I see the condition, prior probability, then this posterior probability is the probability of the event after I see the condition. So that's why they use posterior as opposed to prior in some situations. In other situations, this is a conditional probability. Well, because it's got a condition. This is what we call the marginal probability. It really doesn't depend on the other variable. It's independent, well, not independent, but it doesn't have it in its formula. So it's called the marginal probability. So you can hear this thing called a marginal or prior probability, and this called the conditional probability or posterior probability. But what it is this is the probability of the event without the condition. This is the probability of the event with the condition. This was the probability of picking a white cube, and this was the probability of picking a white cube, given that I found one of the white cubes that fell off out of the box. Okay? Now, let's do it again. Here's our box, 5 cubes. We randomly pick one. The probability of a white one is 3/5. The probability of a black one is 2/5. Nobody's going to complain about that. That's kind of obvious, kind of straightforward. And something falls out. Something falls out of the box. Now, that's going to require a little discussion here. Hello? Something falls out of the box. All right? It's on the floor, and it rolled underneath the couch. We can't see it. I don't know what it is. It's there on the floor. Well, what is the probability that the block, I pick a block, what's the probability that it's a white one? What's the probability that it's a black one? Now this takes a little insight here. I don't know what that is. Let's say they're all there when I pick. This is going to be clear. They're all there when I pick. It's 2/3 chance of it being white, 2/5 chance of it being black, and now someone takes the 4 that's left and puts them in a drawer. Still a 3/5 chance it's white and a 2/5 chance it's black. Well, now someone empties it into the drawer. Someone dumps it somewhere, and one of them falls here, one of them falls there, one of them, but I don't see any of this. They just do that in another room. It's certainly not going to influence the chances that this is a white ball, a white block, or a black block. Still 3/5 and 2/5. Now comes the tricky part. What if the spill was done before I picked? Okay? Now, shake the box, so getting ready to pick, and one of them falls out, but I don't see what color it is. And it's there under the couch. And I'm going to pick out a ball. And there's only 4 blocks in there, and I'm picking one. What are the chances that the block I pick is going to be white? And what's the chances the block I pick is going to be black? Well, that really depends a lot on which one fell out, but I don't know which one fell out. As a matter of fact, since what fell out is sort of random, I didn't deliberately pick one and throw it away, there's a 3/5 chance that I'm going to pick a block that's white. And there's a 2/5 chance I'm going to pick a block that's black. Because I'm still equally likely to pick any one of the blocks. Even though one of them fell out, I don't know which one. I'm equally it doesn't really matter whether I pick first. In fact, it doesn't really matter whether you spilled out 4 of them and left 1 in there. Think of it that way. What if you spilled out 4 and left 1? There's a 3/5 chance that the one that's left is white and a 2/5 chance that the one that's left is black. Well, if I spilled out 3 and I pick 1, it's the same as if there's 1 left. There's a 3/5 chance that it's white, 2/5 chance that it's black. So, 1 falls out. I then have 4 to pick from, but I pick 1. It's equally likely to be any one of the 5 that were there originally, and therefore there's been no change in the probability, 3/5 and 2/5. So whether the blocks fell out before I picked or the block fell out after I picked, it has no effect on the probability, as long as someone didn't deliberately pick out a block and throw it away. So if something falls out, the probability is still 3/5 and 2/5. And it doesn't really matter when it fell out. Okay? Now, what happens if after it falls out and it's rolling under the couch, I sort of stick my head down a little bit, and I see that it's a white one. I see that it's white. Okay? I see that it's white. Only our knowledge has changed. Only our knowledge has changed. And I didn't say when I found out. So let's try and figure this out. What's going on here? Clearly, if it fell out before I picked, then there's only 4 left in there. 2 are white, 2 are black. Probably is a half it's white, half it's black. I don't think there's any problem with that because there's only 4 left and 1 is not eligible. I see it. It's right there. I know it's not it. But what happens if I pick 1 out, put it in my pocket, and then 1 falls out onto the floor? It was 3/5 when I picked it out, being white. But now what's its probability? Well, 1 randomly fell out. It's not eligible to be the one in my pocket. The one in my pocket is equally likely to be any one of the 4 that's not on the floor. Equally likely to be any one of the 4 left. 2 of the 4 are white, 2 of the 4 are black. Therefore, probability is a half that it's white and a half that it's black. It doesn't really matter when I find this out, whether I find out before I pick or after I pick. The condition changes the probability. The condition changes the probability. And it's as if there are 4 balls in the box when I pick. It doesn't matter whether I picked with 5 or not. There are only 4 that's eligible. These 4 are the only eligible one because the one I see there on the floor is not eligible. And so probability of a white one, given that one white one is not there, is a half. The probability of black, given that one white one is not there, is a half. Okay? Interesting. Not trivial, but interesting. Now, the word independence, we've used it many times. What it really means statistically, statistical independence, is that if the probability of an event given a condition is the same as the event, then the condition does not influence the event in any way, and we say the event is independent of the condition. The event does not depend on the condition. If that's the case, if conditional probability equals the marginal probability, or the posterior probability equals the prior probability, then we say the event and the condition are independent of each other. That's the definition of independence. Doesn't really matter what the condition is. Sure, physical independence, most of the time in statistics a word is used that physical, everyday words don't jive with it. But in case of independence, everyday words do seem to jive with it, because physical independence does imply statistical independence. I flip two coins, a penny and a nickel. They're not related to each other. If I get a head on one, it in no way influences whether I get a head or tail on the other. So I can get a head on the penny and tail on the nickel, or vice versa, and no influence. They are physically independent. They are also statistically independent. The probability of getting a head is a half, and it doesn't matter whether I got a head or a tail on the other coin. The condition in no way influences the probability of the event. And so in that case, the coins are independent, statistically as well as physically. But statistically, in order to prove independence, you must show that the conditional probability equals the marginal or prior probability. Okay? If the conditional probability of an event is the same as the prior probability of the event, then the event and condition are independent of each other. That's what it says. If the conditional probability and the prior probability are equal, then the event and condition are independent of each other. Dependence is just the opposite of this. That means if the event and condition are not the same as the probability of the event without the condition, then the condition does influence the event in some way, and the event is dependent on the condition. And an example of that we already saw with the blocks. Seeing that block on the floor is a condition, and the probability of drawing a white or a black cube certainly depended on whether I saw that block and whether it was white or it wasn't white. And the condition influenced the event, the probability of the event, and we say the event is not independent of the condition, it's dependent on the condition. Let's take an example and see if we can't find something that's independent. Talk about independence a little more. Our example is a family with 2 children. If there are 2 children in a family, one is born first and one is born second. The only 4 possibilities are that the first one's a boy and the second one's a boy. The first one's a boy, the second one's a girl. The first one's a girl, the second one's a boy. The first one's a girl, the second one's a girl. And each of these are equally likely, so we feel, let's say they are. They're equally likely. Okay? Now, what is the probability of having a boy second? Well, there's 2 ways to look at it. Most of us just come up and say, oh, a half. But let's look at it. There are 2 ways you can have a boy as a second child. 2 out of 4. If the 4 are equally likely, then 2 out of 4 has probability of half. So the probability of having a boy as your second child is 1/2. Okay? Now, assuming they're equally likely, these 2 are also equally likely. Let's look at those 2. And we're going to talk about what happens when we have a girl first. If we have a condition that there's a girl first, we know the first child was a girl. Well, if the first child was a girl, this couldn't have happened, this couldn't have happened. This or this must have happened. These 2 couldn't have happened. One of these must have happened. So the girl first, the only possibilities are these 2, and they're equally likely. Well, keep in mind what they are. Girl first, boy second, girl first, girl second. And they're equally likely. If that's the case, then the probability of having a boy, given that there's a girl first, is 1 out of the 2, because one of them had a boy second and a girl first. The other one had a girl second and a girl first. half of them, one half of them, had a boy second and a girl first, and if they're equally likely, probability is 1/2. Well, note, the probability of a boy second given a girl first was the same as the probability of a boy second without the condition. The condition in no way changed the probability of the event. So we say that a boy second and a girl first are independent of each other. Boy second, girl first are independent of each other. Of course, that's not a big deal. We would like to be able to say the sex of the first and second born children are independent of each other. And the only way to say that is if all of the possibilities are independent. So let's go and see what we can do. We put the things together. We do this again for every possible combination. And what we find is this, that if you check out boy first, girl, boy second, girl first, that's the same as boy second. Girl second, girl first, that's the same as girl second. Boy second, boy first, that's the same as boy second. The event in no way is influencing. We can find that all of these things, pick any one of them you like, they're actually, in our example, they're all equal to 1/2. Everyone here is equal to 1/2. 1/2. Everything is equal to 1/2. And therefore, they're all equal. And what we find out is that boy second and girl first, they're independent events. Girl second, girl first, they're independent. Boy second, boy first, independent. Girl second, boy first, independent. Boy first, girl second, independent. Girl first, girl second. All the combinations are independent. And when all possible combinations of two things are independent, we say that those properties, those things, the properties are independent. In this case, the sex of the first and the sex of the second born children are independent. The sex of the firstborn was property 1. The sex of the second-born was property 2, and they're independent of each other. Events can be conditions. Conditions can be events. That's because, remember, we worked out things like boy second given girl first. I also had the probability of girl first given boy second. So we can interchange conditions and events, but we'll talk about that next time, interchanging conditions and events. In general, if we want to find independence, we can do this. But if we have independence because the condition and events do not jive in any way, combination, form you like, you will be able to say they are independent things, independent properties, independent factors, if you like. Not everything is independent. Let's go back and I'll show you some things that are not independent. Pick 2 boxes, 2 cubes out of this container here. Pick 2. Not looking, just close your eyes, put your hand in, and pull 2 out. What's the probability that the second one is white? Well, if we don't know what the first one is, we didn't look at the first one, we put it right in our pocket, then we're in that situation where one of the balls fell on, one of the boxes fell under the couch. We don't know what it looks like. Well, if we don't know what it looks like, the one we have is equally likely to be any one of them, and therefore there's a 3/5 chance that it's white. So the probability of the second pick being white is 3/5, without knowing anything, no conditions. This is the marginal of this. What is the probability of the second one being white given that the first one was white? Well, if I know the first one was white, then it's no longer there. I only have 4 to pick from. And if you have 4 to pick from, the first one being white is not there. I have 2 whites and 2 blacks, and therefore the probability is 1/2. The probability of an event is 3/5. The probability of an event with a condition on it is a different number, and therefore they are dependent. What we have here is dependence. The first pick and the second pick are dependent because the probabilities don't match up. All right, what we saw is how to find dependence and how to find independence. It's just playing with the probabilities. The important thing that we learned today is that the condition can affect an event. But if we don't know what the condition is, then it's as if the condition never happened. See, if you say, I have a box, there are 5 things, and someone pulls out one, takes it away, and I pull out a second one, What is the probability that my second one is white? Well, it doesn't really depend on what the first one was because we don't know what it was. And if we don't know what it was, as far as we're concerned, it's in there because we are equally likely to pick any of the ones that are left. That's a little tricky concept, but after a while it'll sink in. It'll become part of your common sense, and then you will understand these things. And we're going to use this stuff next time, so try and remember it for a day. See ya.